our final presentation coming from American Oregon State University. We have Dr. Mahdavifar. So he's going to talk to us about connecting hybrid CLT. Hybrid CLT means the CLT made out of different grade of wood.
So today we are going to talk about the hysteretic behavior of the metal brackets on the hybrid CLT panels. We did this test in the Oregon State University. Right now we have the PRG 320, which is a standard that governs the manufacturing of the CLT panels in North America. This is a standard recommend to use visually graded lumbers for the face layer and the core layer. So in the US, the visual grading grade the lumbers based on the visual inspection, like the knots, cracks, and grain angles and stuff like that. So we have a recommendation for the face layer and the core layer. Based on these things, the PRG 320 gives a table with predefined grade CLT panels that you can see here. On the other hand, in this plot you can see the global production of the CLT panels. So you can see that the CLT production trend is exponentially going up, and on your right hand side you can see a pie chart that shows what is the portion of the panels that are sold in the market as a commodity product, and what is the how many percent, how big portion is for the panels that are made for the custom size for the customers. So having this exponentially growing market, anything that can boost the CLT industry should be interesting for us. So we tried to answer two questions. Is it possible to use and mix low-grade and high-grade material? So the PRG 320 recommends to use no 3 or better for the core layer or no 2 or better for the face layer. So is it possible to mix the lower-grade material with each other to make the hybrid panel, or mixing different species of lumber together to make a hybrid panel? So we think we can do the hybrid panel. So with hybrid panel, I mean a panel that has a mixture of high-grade and low-grade material, or mixed species with different timber. So this is a regular panel, a homogeneous panel. You can see that the face layer and the core layers are the same material, the same grade. But this is a hybrid panel. You can see we mix two different species, in this case Douglas fir and the lodgepole pine. So we think we can do hybrid panels. There are several potential advantages for doing the hybrid CLT. First, it helps to reduce the pressure on the structural lumber supply. Also, it provides an outlet for the low-quality material, low-grade material. And the most important thing, it helps us to reduce the price for the production of the CLT panels. It also helped to revive the forest product-oriented society in North America and help in putting the CLT in the mainstream of the CLT construction. Okay, so having this thing, if you look at the CLT wall, you can distinguish 4 different components of deflection in a CLT wall: rocking, sliding, shear, and bending. So the first 2 components, the rocking and sliding, are found to be more significant. We still have shear and bending. So the rocking can produce uplift, you can see here, And this sliding will produce shear in the connections. So we are trying to answer one question. How can we characterize the cyclic performance of the connection system on hybrid layout? So this work can contribute to the literature on the effect of density, the hybrid CLT, and provided quantitative data for the quantitative data for the performance of the CLT connections on hybrid layout, and a baseline for the calibration of the numerical model for the connection. So we did a test. This is a layout that we used. So we had a hybrid layouts with several layers. We had Douglas fir and lodgepole pine high grade on the face, and we had Douglas fir, lodgepole pine, and hemlock low grade on the core. We also had two layouts of regular panel that had Douglas fir and lodgepole pine. So for these two reference panels, the face and the core were similar. And we used the PRF adhesive, and the clamping pressure was 0.68 megapascal. So here you can see all the 7 layouts that we tested. We have 2 homogeneous panels, so all layers are similar. And we also had 5 hybrid layouts that you can see here. Each panel has a 4 character long tag that gives you what kind of panel is that. So, for example, the first 2 are HD, means high-grade Douglas fir or high-grade pine on the face. And the second 2 characters are showing the material in the core. So, for example, LP means low-grade pine, or LH means low-grade hemlock. So 4 characters long, and in this paper, we are just talking about the result that we got on this homogeneous panel, HDHD, high-grade Douglas fir on the face and core. This panel, high-grade Douglas fir on the face and low-grade Douglas fir on the core. And this panel that has high-grade Douglas fir on the face and low-grade pine in the core. 3 connection systems were chosen, 2 for wall to floor connections, this one and this one, and 1 for wall to concrete foundation connections. Right now, I'm just in this paper, we are talking about this connection that use the CNA 460 nail, which is a new nail in the US. And kind of this is a certification for using that nail too. Okay. This is the SketchUp of the test fixture. We had this test fixture for uplift and this test fixture for shear. So this panel is the floor panel, and this panel is the wall panel, and we are putting the uplift on the panel. In this test fixture, this side is the floor and this side is the wall. So we have the floor and we have the wall and this kind of movement. So for each connection we have 6 degrees of freedom. We constrain all of them except uplift here and the shear. So we had a testing fixture that isolated just uplift in this one and shear in this one. So for loading protocol, we adapted the modified Curie loading protocol. So the modification was in case of the loading rate in order to do each test in 5 minutes. So we had a couple of 100 tests, and if we wanted to do the full Curie, it takes a couple of hours. So this is one kind of modification. The other one was for the uplift, that we had a half non-symmetric Curie. So when you have a wall, it's not practical to go into the other direction. And yeah, this is the picture of a test. So this is the So this is a test that, this is a picture from a test on the behaviour connection in uplift. So this panel simulates the wall, and this panel simulates the floor. And this is the behaviour bracket. So if you look at the nail here, the nails are working in shear loading. And during the test, the nails were almost intact, so we didn't get any significant damage on these nails. But the nails in the other side, in the floor side, were almost pulled out. So this was the most common mode of failure that we observed. And this is the shear test that you can see. This is again the floor side, and this is the wall side, and we had this kind of movement. So on the wall side, you can see that the nail fell in lateral direction, and most of the nail got sheared off in the head. In this side, the nails were working in, they were pulled out. So this is the common mode of failure in shear. This is the result that we got from the test. So I reported 2 different points from the hysteretic behavior. The first one is the peak load and the displacement at peak load. And the other one is the failure load and the displacement at the failure load. The failure load defined when the load dropped for the first time to the 80% of the peak load. So if you take a quick look at the loading here, you can see for the regular panel here, we got this much force, 21.7 kilonewton of the maximum load. And for the hybrid one that has the low-grade Douglas from the core and low-grade pine in the core, we got lower numbers. It's like 10% less. And this is the corresponding displacement for the peak load. So you can see that when we are going to the hybrid panel, the peak load kind of drop. In shear, we get a different story. So this is the peak load, and you can see that the maximum load for all the 3 panels are almost the same, and the same similar thing for the maximum displacement. So the test result suggests that there is no significant difference in the shear direction. So we did the same thing on the, we did a t-test with 95% confidence, and our observation is confirmed. So you can see that in shear, the t-test recommend no difference. So here we are comparing the homogeneous panel with the hybrid panel with low-grade Douglas fir, and comparing the homogeneous panel with low-grade pine in the core. And this is the comparing the 2 low-grade panels. So if you look at these values here, you can see that there is no significant difference between the hybrid panels. But you can see a difference between the hybrid panel and the regular panel in operation. So for loading, you can see the drop. But for displacement, the behavior is kind of mixed, and making conclusion need more inspection. So conclusion: comparing the hybrid layout versus the homogeneous panel, in shear there was no significant difference in case of strength and stiffness between the connections on hybrid and homogeneous. But in case of strength, there was a difference that you can see here. But in case of displacement, there was no. We have seen a mixed behavior. But when we are comparing the hybrid panels with each other, the difference in shear and the stiffness were not statistically significant. The future work we will use the data that we got from the test to do the calibration. We are using some numerical material, like source material, for doing the calibration work, and so that people can use our data for the numerical modeling. We also will do the test on the hybrid CLT full-scale wall test, and we will do the cyclic test on that. At the end, I would like to acknowledge the United States Department of Agriculture for funding the project, and all the people in Oregon State and other companies that help us. Simpson Strongby for providing us with connections, and Hexion and Henkel for providing us with adhesive, and the local companies for providing us with lumber for making the panel. Thank you.
Questions for 5 minutes?
So in a hybrid panel, the specific gravity or the density of the middle layer is different than the surface layers.
Yeah.
So how would you characterize density or specific gravity for fastener design? Do you characterize that based on the lower specific gravity of the core, or on the higher specific gravity of the surface?
So, in capturing the strength of the single fastener, there are, in lateral direction, we have European Youth model, and it's based on some assumptions that the strength, and the density of the substrate material is same over the length of the fastener. But for hybrid nails, hybrid fasteners, probably we should modify those equations and consider the effect that there is a higher density in the top part of the nail and lower density in the root of the nail. We should consider that, but it's not presented in this paper yet.
If there's no questions, let's give another round of applause to our wonderful presenters.